All right, let's talk about solving polynomial functions. First thing you need to do to be able to solve a polynomial function is to be able to set your function equal to 0. So if f of x is equal to this mess here of 10x cubed plus 80x squared plus 160x, let's set it equal to 0. Because if we set it equal to 0, replace f of x with 0, we can use the zero product property. Okay, so that means if I can factor this, get it into its factored version, then I can find the solution. So I'm going to look at it and I can say, well, I know 10, 80, and 160 I can take 10 out of. Okay, x cubed, x squared, and x I can take an x out of. Okay, so 10x times what is 10x cubed? Well, that's x squared. 10x times what is 80x squared? That is 8x. And 10x times what is 160x? That is 16. And then once I have that, and remember, all that equals 0. Okay, so once I have that, I can then look at this chunk right here, the x squared plus 8x plus 16, and factor that. So I now have 0 is equal to 10x, but I know x squared plus 8x plus 16 factors to x plus 4 times x plus 4. So I'm assuming you can factor okay here. And from there, I can set, since I have 3 factors, I can set each of those factors equal to 0. So I can say, well, if 10x equals 0, then x has to be 0. Okay, if x plus 4 equals 0, well, then x has to be negative 4. And that actually occurs, that negative 4 occurs twice because it happens here and here. So another way of writing this, by the way, is 0 is equal to 10x times x plus 4 squared. Okay, the squared means it would appear twice. All right. So what this means is I have multiple zeros at negative 4. So now, if you have repeated solutions or multiple zeros at a place, and there are an even number of those repeated solutions, like in this case 2 repeated solutions of negative 4, so we have x equals negative 4 and x equals negative 4. We have it 2 times. Okay, that's an even number of repeated solutions. And that means my graph is just going to go up and touch that point on the x-axis and then change directions. A lot of times we call that a bounce. Okay, so if I was to graph this, I can say, well, I know it's an odd degree. It's a positive a term, so I'm going to be up, down. I'm going to go up. I'm going to hit negative 4 on the x-axis, and I am actually going to change directions at negative 4. So my graph could start down here somewhere. Okay, hit negative 4, and it can come back down, and then it's going to go back up through 0, and then end up somewhere up there. Now this is only accurate at my zeros and my end behavior, but that's essentially how my graph is behaving. Okay, now let's say they're an an odd number of repeated zeros, so maybe negative 4 appears 3 times, or better yet, let's go ahead and take and use a different function, like let's say I have negative 10, f of x equals negative 10 times x minus, let's just use or x plus, 1 cubed. Okay, so in this case, I know that x plus 1 cubed really means negative 10 times x plus 1 times x plus 1 times x plus 1. Happens 3 times. Okay, so this would give me a 0 of x plus 1 equals negative 1, and this would give me negative 1 as well, and this one would give me negative 1 as well. So I'd have x equals negative 1 there, x equals negative 1 here, and x equals negative 1 right here. That should see 0. I'm sorry, I got ahead of myself here. So x plus 1 equals 0, so that gives me negative 1, negative 1, and negative 1. That means I have negative 1 3 times, an odd number of times. Well, if that happens, if the odd number repeated solution, it goes through the graph, that point on the x-axis, and it's an inflection point that does not change directions vertically. So in other words, my graph will actually, since it's an end behavior, well, it's a negative a term, so it's going to be down or excuse me, up and then down. Okay, but it's going to come down here and hit -1. It's just going to change direction. So inflection kind of, say my graph starts up like that. It's like a half parabola, and then I get to this point, and then I kind of go downward. Okay, let me make that a little better. Okay, and then I'm going to go through the y-axis at some point way down here. Okay, so this would happen at -1. It's a point of inflection right there. All right, in fact, the y-intercept on this one would be 1 times 1 times 1, which is 1 times -10, or -10. So maybe down here somewhere where it hits the y-axis is at -10. Okay, so just a quick reminder of graphing and what it looks like with repeated solutions. All right, let's go ahead and find the zeros of a polynomial function and then graph it. So the first thing to do is note what format you're in. You have a trinomial, you have x to the fourth, x squared, and nothing, so you can't take anything out that way. You can pull out a 3 to begin with. 3 times x to the fourth minus 20, or minus 8, x squared plus 16. Okay, and then I can, that's f of x. I then can look at it and say, well, x to the fourth, x squared, this power is twice that power. So if I could break it into the format of ax squared plus bx plus c. So in other words, something raised to the second power and something raised to the first power. Right now I have raised to the fourth and raised to the second. That could be helpful. So I could look at it and say, well, I know that x to the fourth is actually just x squared. And I know that x squared can be written as x squared to the first, and I have my 16. Now I know that looks weird, but stay with me. If I didn't know what was in here or what was in here, I would have something squared plus or minus 8 times something to the first. Just like I want here, something squared and something to the first. So really, I do know what's in there. I mean, we know that. We know you have x squared in there. Okay, so what I'm going to do is I'm just going to say, well, I'm not going to call it x squared anymore. I'm going to say x squared is equal to u. So wherever I have an x squared, I'm going to put a u. Okay, so I'm going to have u to the second minus 8 times u plus 16. So this x squared became u. This x squared became u. I have that squared on the outside. By doing that, that allows me to easily factor this. U squared minus 8u plus 16, that just factors to u minus 4 and u minus 4. And then I can go ahead and put that x squared back in. So I just put that u in to help me see it a little easier. And then I can replace the u with x squared again. So u now is back to x squared. Now some people don't need to do that, but I do. It helps me out. Okay, and then I look at x squared minus 4. Well, that's difference of two perfect squares. So that's x plus 2, x minus 2. And this x squared minus 4 is also x plus 2, x minus 2. And I have my 3. And remember, the whole reason I'm trying to get this all factored like I have is because the zero product property means if I plug 0 in for f of x, I'm trying to find things that multiply to make 0. So now I've got 5 factors. Well, 3 is never going to be 0 because there's no variable next to it. But I have x plus 2, and it appears twice. Right there, right there. And I have x minus 2. It appears twice. And so really that's just means that when I'm solving this, I can say, well, x plus 2 equals 0. Well, where does x plus 2 equal 0? X plus 2 equals 0 at negative 2. So that means negative 2 is a solution twice. And here I have x minus 2 equals 0. Where does that happen? Well, x minus 2 equals 0 at 2. That appears twice. Well, this is a 4th degree polynomial. Okay, that means I could have up to 4 possible solutions, and I do. I have 2 appearing twice and negative 2 appearing twice. My solution solutions are plus minus 2. It just so happens that the 4 solutions are in the form of 2 answers. Okay, so it crosses at -2, or it hits at -2, and it hits at 2. I know it's a 4th degree with an A term positive. That means it starts up here. It ends up here. Okay, it's an up. Okay, I know that it's an even number of repeated zeros at -2. So it's just going to come down and hit. It's an even number of repeated zeros at 2. So it's also going to come down and hit. And in this case, we're just going to kind of carry it up here. Okay, and I know my y-intercept. Why don't we go ahead and carry this one up as well. Okay, I know my y-intercept. In this case, it's 48. It's my constant. It's when x is 0. So if I go up by 10, so 10, 20, 30, 40, 50, 60, 70. So 10, 20, 30, 40, 50. So right about there is 48. This graph's going to come up. It's going to hit right there, and it's going to come back down. Okay. Y-intercept of 48. That's our approximate graph. All right. Well, the next thing is the rational roots theorem. And the rational roots theorem helps us to kind of figure out exactly what some possible solutions are. So I'm going to show this in a couple different ways. First, I need to point out the word factor is spelled wrong here. That's ridiculous. F-A-C-T-O-R. Okay. But it says, hey, if you have this whole junk right here, this is just a polynomial. So if you have a polynomial, that's a mathematical way of writing a polynomial. Okay, when you see that, that's what it means. Okay, so if you have a polynomial which has integer coefficients, meaning any positive or negative number, then every rational solution, rational, remember, means every fraction. It could be expressed as a fraction. So any solution that can be expressed as a fraction. So that means the ones that can't be are like pi or root 5 or root 7, any of the imperfect roots. Then every rational solution of f of x equals 0 has the following form. P divided by Q, where P is the factor of the constant term, a sub 0, and Q is the factor of the leading coefficient, a sub n. So really, what it's saying is if you take any polynomial function, so let me just take one for example, f of x is equal to 3x cubed plus 2x squared minus x plus, let's say 6. Okay. Better yet, let's say 8. Okay. So that would mean here would be P. Your last term is P. Your front term is Q. Okay, so really you're looking at these. So all of your possible solutions are P over Q. All the factors of P over Q. So the factors of 8, like 1 times 8, 2 times 4. Okay, those are all the factors of 8, with the exception that it's just not 1 and 8, it's actually positive 1 and negative 1 times positive 8 and negative 8, right? Because you could have 1 times 1, or 1 times 8 is 8, or negative 1 times negative 8 is also 8. Okay, so that really means you always need to put plus and minus in them. Positive negative 2 and positive negative 4. Okay, because you can make those situations. And here I could have positive negative 1 and positive negative 3. Okay, so I could have a solution. Well, I could have all of these because each one of them could be divided by 1, which wouldn't change them. So possible solutions for this. I don't want to confuse this with the next problem, but so let me go ahead and give myself some room here. These are possible solutions. Well, it could be positive negative 1, positive negative 2, positive negative 4, and positive negative 8. So all of these. And then I'd have to divide them. That's by dividing them each by 1, by the way. I just don't put the 1 under them. And then I have to divide each by positive negative 3. So I could have positive negative 1 over 3, positive negative 2 over 3, positive negative 4 over 3, and positive negative 8 over 3. Those are all the possible solutions. The rational roots theorem just helps us to figure out a possible solution. Now, I will tell you that as I'm doing this, I always test for 1 first, because 1 goes into everything. And a quick way to test for 1 I'll show you with this problem. So find all the real solutions of f of x equals x cubed plus x squared minus 5x plus 3. Well, first thing, can you factor? No. Can you use factor by grouping since there are 4 terms? Yeah, it doesn't work. You could try it, it doesn't work. So we're going to set it equal to 0. I'm going to make f of x equal 0. And I'm going to look at this and say, okay, what are some possible numbers that can go into this? Well, how could I know? Well, I know my first value, or q, is 1. Okay, well, that's nice, because then I don't have to deal with all these extra thirds and stuff that I had because I had that 3 there. But then I also have my last term is 3. So I know that any possible real or rational solutions have to be factors of 3. So there's only 2 factors of 3. There's positive negative 1 and positive negative 3. So I guess there are 4 factors of 3. Okay, so I'm going to test for 1 because that's the easiest one. And the way you do that, the way you test for 1 is you just add your coefficients up. Right? 1 cubed is still 1. 1 squared is, well, that's 1. 1 times negative 5 is negative 5. And 1 times, well, there's nothing there, so that's just 3. So 1 plus 1 minus 5 plus 3. Well, that equals 0. Well, that's good, because if your remainder is 0, then that means it's a solution. That means if I do synthetic division right here, if I said, well, I think 1's a solution, and I put 1, 1, 5, negative 5, and 3, and then bring this down, well, that's 1, and that's 2, and that's 2, and that's negative 3, and that's negative 3, and that's 0. That's good. That means this answer, which is x in the form, that form is x minus 1. That's what makes a positive 1 as a solution. And this is x squared plus 2x minus 3. All equals 0. So we have now factored this to become that. And so now I can look at factoring my quadratic here. So all of that can become, well, 0 equals x minus 1 times, well, that factors to x plus 3, x minus 1. All right. So that means my solutions actually are x minus 1, quantity squared, times x plus 3. So I have a solution of x minus 1 equals 0, or x equals 1, and that appears twice. And x plus 3 equals 0, or x equals negative 3. So writing it out, we only have to list the 1 time, unless it asks for its multiplicity is another way, or repeated zeros. There we got it. All right, well, let's go ahead and try another one here. All right, finding zeros of polynomial function. So find all the real zeros of this function. 3x cubed plus 9x squared plus 4x plus 12. First thing I'm going to do is set this part equal to 0. Okay. Notice I put a little thing here. It says test all the factors of the constant term first, and then, if needed, divide by the leading coefficients factors. So I'm just going to list all the factors of 12. Okay, so positive negative 1, positive negative 12, positive negative 2 times positive negative 6, 3 times 4. Okay, so those are all my possibilities. All right, so I'm going to test all of these before I start dividing by 3. Okay, so just because that's easier if it works out. So I look at it and go, okay, well, does 1 work? Well, remember my test for 1 is really fast. I can just add up my coefficients. So 1, 9, 4, and 12. Well, they're all positives. Well, that's not good, because when I'm adding a bunch of positive numbers, there's no way I'm getting 0. In fact, by knowing that these are all positive, that helps me to rule out any positive number here. So I know, like if I'm making my list, I know 1 won't work, I know 2 won't work, I know 3 won't work, I know 4 won't work, I know 6 won't work, and I know 12 won't work. None of the positives will work because I can't plug in a positive and get a 0 if I'm adding up here. And there aren't any negatives. So let's try some negatives. Let's try -1. Okay? So -1. Well, -1 just flips the signs of the odd function. So -1 times -1 times -1. Well, this is -1 times 3, which is -3. -1 times -1 is 1 times 9, which is 9. So it's still positive 9. -1 times 4 is -4. So notice just a quick another shortcut. If you're testing -1, you're just changing the signs of your odd degrees. So -3 and -4 is -7, 9, and 12. So it still doesn't work. This one will not work. So that doesn't work. None of the positives work. And now -1 doesn't work. Let's try -2. And I'm going to go ahead and use synthetic division. Try -2. Okay. So I'm going to put my 3, my 9, my 4, my 12. Okay, drop 3. That's -6 now. 3 gives me -6 again. That's -2, and that's 4, and that is 16. So I have a remainder of 16. -2 does not work. Let's try -3. All right, -3. Test them again. 3, 9, 4, 12. Okay, drop that 3 down. 3, -9, 0, 0, 4, and hey, there's one that works. I get a remainder of 0. So that means x plus 3, that's how we get the -3, times 3x squared plus 0x minus or plus 4. And that is equal to 0. So this whole thing has factored to that. Okay, so we've now factored it. We've got it down to a quadratic. And in fact, since I don't have a b term, that's a real easy thing to solve. We know that x plus 3 is easy to solve, but this is just 3x squared plus 4. So no b term, don't even have to factor. X plus 3 equals 0. We know that is a solution of -3. We already figured that out. Okay, and from here, 3x squared plus 4 equals 0. Well, that's 3x squared equals -4. X squared is equal to -4 thirds. And then we got to take the root. So x is equal to plus minus square root of -4 thirds. Okay, well, here's a problem. All right, because this says find all the real solutions. These solutions right here, that is not real because it has a root of a negative. These are imaginary. Okay, this one's real. Okay, so x equals -3 is real. So the real solutions here are x equals -3. That is the only real solution. That means it's the only one that would cross the x-axis. Graph this, I would know that, well, it's an odd behavior. Excuse me, it's an odd function. So it would have a down-up, okay, and it would cross at -3. So it would come up, cross at -3. It'd probably do some kind of weird stuff in here, and then move back up. Okay, I don't know exactly. I know it would cross also at 12, the y-intercept, right? A constant. And here is -3. Obviously not to scale, but it's a quick sketch there. Okay, it would only have one x-intercept. All right, well, let's go ahead and try another one. Finding zeros of polynomial functions. So find all the real solutions of x cubed minus 5x minus 4. All right, so on this one here, once again, I'm going to try, first I can't do anything. I can't factor. I can't, this is a third degree. That's a first degree. I can't do quadratic or form factoring for quadratics there. So when I'm looking at it, I'm going to try to find all the zeros of the back function, or the constant term there. So positive and negative 1 times positive negative 4, positive negative 2 times positive negative 2. Okay, so I'm going to test 1 again, and I kind of mentioned the shortcut in testing 1 earlier, where you just add up your coefficients. So 1 minus 5 minus 4, well, 1 minus 5 minus 4 does not work, so 1 is out. So I can try negative 1. Well, remember, the negative just changes the odd degrees. So rather than being positive 1, it's negative 1. Rather than being negative 5, it's positive 5 and negative 4. Well, that appears to work. Negative 1, positive 5, and negative 4 is 0. So let's go ahead and just double check that with synthetic division. Let's try negative 1 here. We're going to put our 1. Notice I don't have an x squared, so I have to put a place value holder for x squared. Negative 5 and 4. Drop that down. I get 1. Negative 1 times 1. Negative 1. I get negative 1. That gives me 1. Negative 5 plus 1 is negative 4, and gives me, oops. Oops, that's supposed to be a negative 4. I was like, man, that's not going to work. Negative 1 times negative 4, that's positive 4. Good thing. I messed up and then had that negative, and that gives me 0. So I now have x plus 1, that's this piece, then x squared minus x minus 4. All of that equals 0, so this whole thing has been factored to that. And so then I look at it and I go, well, can I factor this? I cannot. So I know from this chunk I get a solution of x plus 1 equals 0, and I know that I'm just kind of being redundant there, but that's negative 1. This one I have to use either quadratic formula or completing the square on. So I'm going to use quadratic formula. So remember, quadratic formula is x equals opposite of b plus minus square root of b squared minus 4ac all over 2a. Okay, so if I'm thinking of this in terms of a, b, and c, a is 1, b is negative 1, c is negative 4. Okay, so quadratic formula on it, x equals the opposite of b, so 1 plus minus square root of b squared, so negative 1 squared, minus 4 times 1 times negative 4, all over 2 times 1. That gives me 1 plus minus square root of 1, and that's plus 16 over 2, or 1 plus minus root of 17 over 2. Okay, so those are my other two solutions here. So this part gives me a solution of x equals that. So x equals here 1 plus minus root 17 over 2. All right. Well, those are my real solutions. Okay, so I guess if I'm putting it in nice, neat format, there we've got it. Okay. Well, let's go ahead and take a look at something else here. We saw a radical in that last problem, and whenever you're dealing with radicals, you always kind of have that plus and minus piece, and I'm going to show what that means. So we have the irrational conjugates theorem. So it says if f is a polynomial function with irrational coefficients and a and b are rational numbers, that root b is irrational, such that root b is irrational. If a plus root b is a 0, then a minus root b also is a 0 of s. So if I went back to that previous problem, notice right here we could actually write this as x equals 1/2, so that's divided by 2, times 1 plus minus root 17. So here's our a plus our our a plus our root b. So it's just saying, well, if I know that 1 plus root 17 is a solution, then I also would know that 1 minus root 17 is a solution. Okay, and notice that that's true. These are both solutions. I got the 1/2 because I got rid of that divide by 2. So rather than divide by 2 and multiply by half. But that's true there. That's what the irrational conjugates theorem is saying. So let's try it with a problem here. It says write a polynomial function f of the least degree that has rational coefficients, a leading coefficient of 1 and the zeros of 2 and 3 root 7. So it means coefficients means all my numbers have to be either fractional or whole numbers. Okay, so rational coefficient, they can't be like roots or pi. Okay, so but my zeros, they're saying it has a 0 of 2. And remember, if something has a 0 of 2, that means in factor form that would be x minus 2, because x minus 2 when set equal to 0 would give me an answer of 2. And 3 root 17. Well, 3 root 17, how do we write that? Well, that means x minus 3 root 17. Or 3 plus root 17, excuse me. That's not root 17, it's 3 plus root 7, my goodness. Okay, I'm going to put that in parentheses. Okay, and then remember, the irrational conjugates theorem just says, well, if 3 plus root 7 is a solution, then I automatically know that 3 minus root 7 also has to be a solution. Okay, so let's actually write that correctly. Which means another piece would be x minus 3 minus root 7. Now notice I put that in parentheses. So we always, if we have an answer here, so like this gets a little confusing for students, this part that I just did here. So I'm going to take and I'm going to pretend like I don't know what's there. And once again, pretend like I don't know what's there. Okay, so if I wrote something in factored form and I said all this equals 0, you would go, well, okay, well, this would be x equals 2. And this would be x equals whatever that is. And this would be x equals whatever that mess is. Well, that mess is that, right? 3 plus root 7. And that mess is that, right? It's 3 minus root 7. So that's the reason I put it in that format. I have to put the minus because I have two terms in here. Now, when I'm writing my equation for this, what I could do is I can, first I'm gonna set it all equal to f of x. And I'm gonna go ahead and switch back to this color here. Okay. And I'm going to go ahead and I'll keep that x minus 2, but I'm also going to distribute this negative. So this is going to be x minus 3 plus root 7. And this is going to be x minus 3 plus root 7. I'm sorry, this is x minus 3 minus root 7 here. Okay, distribute the negative. And distribute the negative, so negative times negative is positive. Now notice I have I'm going to ignore this piece right here for a minute. I'm going to multiply trinomial, so 1, 2, 3 terms by trinomial, 1, 2, 3. And a quick way to do that is to just use like an area model. So if I said I have x, negative 3, and negative root 7. And then down the side I have x, negative 3, and positive root 7. Now, if I want to multiply this, very easy to do using an area model. Okay, and so, oops, let's go ahead and fix that. X times x, x squared. X times negative 3, negative 3x. X times negative root 7 is negative x root 7. Negative 3 times x, negative 3x. Negative 3 times negative 3, 9. Negative 3 times negative root 7 is 3 root 7. Root 7 times x is root 7x. I'm sorry, x root 7. Root 7 times negative 3 is negative 3 root 7. And root 7 times root 7 is 7. And it's negative root 7 times 7. So root 7 times itself is the 7. And negative times positive is negative. So I look at this now. I have x squared. So from this stuff right here, I get x squared. And negative 3x and negative 3x is negative 6x. Okay. And then I have this negative x root 7 and this positive x root 7, they cancel. This negative 3 root 7, this positive 3 root 7 cancel. I have 9 minus 7 is positive 2. So that whole piece becomes, that mess becomes x squared minus 6x plus 2. And I'll bring down that x minus 2 there. And now all I have to do is multiply a binomial times a trinomial. Doing that, x times x, x cubed. X times negative 6x is negative 6x squared. And x times 2 is 2x. And negative 2 times x squared, negative 2x squared. I think this is supposed to be 6x squared there. Sorry. So negative 2x squared. Negative 2 times negative 6x is negative 12x. Excuse me, positive 12x. Negative 2 times positive 2 is negative 4. So that gives me x cubed minus 8x squared plus 14x minus 4, all equals f. Oops. Cannot write the f because I keep hitting f. Well, I'm going to have to write that over here. All right, there we got it. X cubed minus 8x squared plus 14x minus 4. All right, I know this got kind of messy right here, but I think we'll be able to be okay here. So that times that, that times that, and that times that. That is supposed to be an x cubed there. Okay, very good. Hope that helps. Good lucky.